Okay, the last type curve method that I want to talk about is the transient method. And the transient method is a little bit of a departure from what we're used to seeing. For instance, and I'll just get rid of that arrow for a second here. For instance, in the transient method, we have one single transient stem and a whole series of different boundary stems. We're not really used to looking at things this way. If you go back and look at Blassingame and Aggarwal-Gardner, there's always only one boundary stem and a whole series of transient stems. So what is it that we're actually doing in the transient format? If you recall, when we look at the boundary-dominated flow solution, and this is back from the theory discussion that we had before, there are different geometries of systems that we can consider. And again, this is just the simple vertical well in a circular reservoir, what I'm going to call the radial model. And what really matters is the ratio of the big circle to the small circle. The layout of these type curves is based on the assumption of how these ratios change. So when I have a whole series of these stems that all merge into one boundary-dominated stem, what I'm doing is I'm keeping the outer circle fixed in radius and increasing or decreasing the size of the inside circle. Okay, and that's what's generating these different type curves. That's Blassingame, Aggarwal-Gardner, NPI. In the transient case, I do it differently. I still have these changing ratios, but in this case, I'm keeping the inner circle the same and changing the size of the outer circle. Now, if you really think about it, if I take the green case in both of these and get rid of all the other type curves, the solutions are identical. They're the same type curve. The only thing that matters is how I'm plotting each one in relation to the others. Okay, in this format, I'm aligning all the transient stems so that the boundary stems will fan out in different locations. In this case, I'm aligning all the boundary stems so that the transient stems will fan out in different locations. So it's a subtle change. It doesn't change anything to do with the underlying model. It just changes how I'm plotting the type curves relative to each other. And why do I care about that change? Why do I need to do that? Well, it makes it a lot easier. And again, I'm going to switch to the transient example for this. Because, as the name suggests, we want to do this for transient data. If we have boundary-dominated data, it doesn't make much sense to go to this transient model. So this will be one that we don't use on all wells. We're just going to use on key wells where we've identified that we haven't seen the boundaries yet. So what I'm going to do is match the data as best I can. And since there's only one transient stem, there should be a unique location for this match. And basically, it makes the type curve matching process easier because I've only got one place to match it because there's only one single transient stem. If we went back and look at Blassingame, Aggarwal-Gardner, we'd see there's lots of transient stems and presents somewhat of a non-unique match. It makes it a little more difficult to find the place where that thing really belongs. Now, of course, I can't get past the difficulty that I had before, and that difficulty is which one of these boundary stems does it really belong to? Well, that one looks like it's not going to fit. The data is already exceeding that stem, so that one's too small. But if I start to pick larger ones, what I'm going to see, and I'm just moving the data as far to the left as I can because I want to illustrate a point here. If I start to pick successively larger stems after this, these are all non-unique solutions. But I could call that one a minimum, but the solution could be there, or it could be there, or it could be there, or it could be even larger than that. So the transient type curve match gives me a very nice way of expressing uncertainty in original gas in place because I can look and find out where the minimum is. Again, the minimum looks like it was at about the RAD equals 48 region. That gives me 3.5 BCF. And then from there, I can extend that, pick different boundary stems that are larger. And I can run production forecasts from each of these interpretations and find out how the reserves are increasing with increasing size of, drainage area or drainage volume. So the transient type curve method allows me a nice, concise way of expressing the non-uniqueness of transient flow on a type curve match and show some different solutions with a minimum gas in place or oil in place and successively larger volumes after that. Again, the transient solution for permeability in skin should be fairly unique in this particular case. Okay. In the transient presentation, we also have finite connectivity fracture type curves. And these were developed by Agarwal and Gardner. And these can be useful if you've got, again, tight gas and large fractures. So in a lot of these systems that are being drilled, wells that are being drilled now, we've got ultra-tight reservoirs, and we put massive hydraulic fractures inside them. And in many cases, these fractures have finite connectivity. So we end up wanting to be able to model that early time behavior and interpret the FCD or dimensionless fracture connectivity from these curves.